Welcome back. Okay, up until now, we've been talking about balanced truncation, which is an effective strategy of model reduction. So if you have a lot of a high-dimensional system with a lot of states and you want to get a reduced order representation in terms of the most important states so that you can control it faster, we can use balanced truncation. So the basic idea here is I have some coordinate transformation, x equals t, z. X are my original coordinates, z are my new balanced coordinates, and t is my balancing transformation. This is an invertible square matrix T, so that in my new coordinates, my controllability Gramian equals my observability Gramian equals a diagonal matrix where these diagonal entries go from biggest to smallest. So most controllable and observable to least controllable and observable. That was the whole framing of a balanced truncation until now. And if you remember, one way that you can actually derive this T transformation is I could take my controllability Gramian from my original system in my coordinates x times WO, again, my observability Gramian in my original coordinates x, and I could compute the eigendecomposition of this super big n by n matrix of Gramians. Now, it's super interesting math that you can do this, the balancing transformation. It's rock solid. We worked through it all. We coded it up. It works. But computing Gramians is extremely expensive. These Gramians, the way people normally compute them is as the solution of a Lyapunov equation, which I think scales something like order n cubed, or it's really an ugly scaling to get these. So if n is big, even moderately big, like 10,000 or 100,000 or a million, computing these WOs and WCs is very, very hard, almost intractable, and computing the eigendecomposition is also really nasty. Okay, so long story short, this works great for moderately large systems, like maybe I have 1,000 degrees of freedom. Back when this was developed, people were thinking about things like aerospace structures like the Space Shuttle or the International Space Station and the Hubble Space Telescope, where you might get these vibrational modes in the structure, but you could write down a pretty decent model in terms of maybe 1,000 or a few thousand components, okay? Now we're thinking about applying these to much bigger systems in turbulence, neuroscience, disease modeling, where you might have millions or billions of degrees of freedom. And so going through this kind of standard procedure of computing your Gramians and then balancing is intractable. Okay, so there were a lot of innovations. Remember, this was more 1981. And so I'm going to tell you in the next few lectures about some of the major innovations that came afterwards that made this tractable for very, very large systems with a huge N. Okay. So to get into the nuts and bolts of how this actually works, I'm going to introduce a system. I'm going to switch to discrete time. The only reason I'm switching to discrete time is because the matrix math becomes a little bit simpler. I don't want you to think too hard about this, okay? What we're going to do is we're going to have x at time step k plus 1 equals some discrete version of my A matrix times x at time k plus b u at time k. And what we're going to have is y equals c at time k as well, okay? Good. And I think something else important here is looking at the adjoint system, okay? So the adjoint system here, this is basically my dynamics written in discrete time, so time step k delta t. And these A, B, and C matrices are different than my original A, B, and C matrices, but there's formulas for how to get these. And if you want to do this in MATLAB, there's a super simple command called C2D, continuous to discrete. Or you can go check the control boot camp for how to go from a continuous time system to a discrete time system. Anyway, this will make it a little bit easier. This is my direct system. I have something called an adjoint system. So a lot of what I'm going to tell you about right now is applicable to systems that you can simulate in a computer where you have the equations of motion, but they're really big. So if I have these equations of motion, I can write down an adjoint system. I can't do this in an experiment. This I can do in an experiment. I can have a high-dimensional nonlinear system that I can control and measure. But what I'm going to show you now is only doable in simulations. So what I could also do is I could define a new system, xk plus 1. And basically, I'm just going to transpose everything. So now this becomes A complex conjugate transpose xk. plus the complex conjugate transpose of C times yk. And I'm actually going to just even erase this output equation. So for now, all we're thinking about is big simulations. Maybe I can simulate the climate or a disease spread or a turbulent fluid. So I have a big simulation code that can do this. I can kick it with U's, and I can measure Y's. So if I give my system an impulse in U, I can measure how that rings through the dynamics of the system X. And then this adjoint system, this is called direct. My adjoint system is basically if I complex conjugate transposed my dynamics, then my output Y becomes the input in these adjoint equations. And what I can do is kind of this thought experiment, a numerical simulation where I impulse my measurements Y, and I see how in kind of adjoint dynamics those ring through and lead to a state X. So this isn't forward time and backward time, but the way I kind of think of it is if I kick U, I measure what happens in time in X. And then what this adjoint system tells me is what states are most excite my measurements Y. So if I have like a delta in my measurement Y, what is the state's history in time that most excites that measurement Y? This is a mathematical construct. You can only do this in simulations. This is fine in experiments. You need simulations to do the adjoint stuff. So everything I'm telling you about is model reduction that people generally do in high-performance computing contexts. OK, good. Remember, fundamental central challenge. Let's write down the central challenge is that I don't want to ever compute WC or WO or do this n by n eigendecomposition. This is nasty, OK? Computing these Lyapunov exponents is really terrible. So what you do instead is you use basically impulse responses of the direct and adjoint system. Now, remember what an impulse response is. Let's say I have an airfoil. I have some airfoil. Let's see if I can still draw an airfoil. OK, airfoil. What an impulse response is at time k equals 0, I'm going to impulsively kick the system. I'm going to impulsively kick it. Maybe I'll give it an angle of attack or something like that. And then I watch how the dynamics evolve through the states of X. So I impulsively kick this thing up, and then I measure how the dynamics go through the state X in time. So this is a movie now of how the state is evolving in time after I kick the system. That's an impulse response. Impulse response. And the kind of bizarre thing is you can do an adjoint impulse response. I can take this little imaginary measurement. Maybe I have a sensor here. And what I can do is I can give this an impulse in that sensor in this adjoint system, and I can measure what states, what the dynamics do to that, and what state history maximally informs that measurement. Very interesting stuff. And if I do this, what I end up getting are these two matrices that essentially look just like the controllability and observability matrices from the control bootcamp before. Okay, so I have this curly C. And what curly C in discrete time, if I give this thing a delta function, an impulse at time 0 with 0 initial condition, my state history starts looking like it's an impulse, so it looks like B. Then it gets multiplied by A. Then it looks like A, B. That's what X looks like at the next time step. Then A squared B, dot, dot, dot. And then A to some power M, B. And I'm just, I'm basically going to kick my system, and I'm going to watch M plus 1 frames of this movie evolving. And each of those I'm going to stack into a tall column vector of dimension n into this big matrix. So this is a big matrix. Every column is a state of my system as time increases after my impulse response. And I can do the same thing with this adjoint system, and I get this thing called the observability matrix. This is kind of the discrete time version of the observability matrix, which is CA dot, 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 CA again to the M power. So this is kind of cool. What we find is that I can, I have my high dimensional system, but I can conduct experiments, numerical experiments, simulations. I can give this thing impulses in my inputs U. I can give this thing impulses in my sensors Y. And I can construct these two matrices, this controllability and observability matrices, purely from simulation data. So this is still data-driven driven by a simulation. And so now what we're going to be able to do is approximate these gramians. These were really hard to compute using the Lyapunov equation. So instead what we're going to do is we're going to say that WC is approximately equal to this controllability matrix times its complex conjugate transpose. Again, for real matrices, this is just a transpose. And WO is approximately, I think it's O star O. Again, complex conjugate transpose for real matrices, just a transpose. So C times C transpose, O transpose times O. And you can verify for yourself. Basically, what I would like you to do as kind of an exercise or a homework is write down C times C transpose, multiply it all out, and verify for yourself that this actually looks a lot like the terms in the controllability gramian. Okay, so this is in discrete time, so there's a few caveats here. Remember, my controllability and observability gramians are smooth integrals from time equals 0 to infinity. So this will be a good approximation. This is good when two things happen. When the delta t is small, so I remember I'm doing this discrete time system. When I have a really small delta t, I'm essentially getting a Riemann approximation of that integral of the gramian using these products. And that Riemann approximation will get better and better when my delta t is small, and when m is large. So basically, when I have enough snapshots that I'm actually approximating this integral from t equals 0 to infinity. Okay, so I'm basically doing a Riemann approximation of my gramians, and if my delta t is small and I integrate for long enough, I get a good approximation. And this is really cool, because what this means, this is what Moore showed, basically. Moore in 1981 showed that I can construct these are called your empirical gramians. Okay, these are empirical gramians because they're data-driven. You run a simulation of your direct and adjoint system, you get this, and you can build these approximations of your gramians without ever doing a Lyapunov equation solve, which is really, really expensive. So this is, believe it or not, cheaper than what people were doing before. Then I can multiply these and find t. And Moore also built in that you could use the principal component analysis to essentially get expressions in terms of the dominant principal components of these structures. So it's interesting, Moore still went through this procedure and constructed n by n controllability and observability gramians, and then computed an n by n T matrix. So that's still very expensive for large n. This is a way of doing it, but it's still very expensive. Wilcox and Pereri in 2002 essentially showed that what you could do is compute a rank R truncation of these gramians before you compute this eigendecomposition. So instead of computing this n by n huge matrix, rank n invertible T matrix, they compute like a rank R approximation and only directly get the R most important columns of T, because that's all we wanted in the first place. We're going to truncate this. So we're computing this T just so that we can throw away most of the columns and only keep the first R components. And so this was a way of basically accelerating that and not wasting a bunch of computational effort computing all of T. But then afterwards, in 2005, Rowley 2005 essentially showed that you could kind of bypass even cooking up these gramians in the first place. And that's what I'm going to tell you about now. So these are both of these methods are called BPOD. And these are both very kind of important additions. After Moore 1981, these made it so that you could scale to big systems. I'm going to show you about kind of this method where you don't have to compute any gramians at all. I encourage you, there's a lot of stuff that happened between 1981 and 2002. So I think you had work by Lal and Marsden and Glavoski and others, lots of interesting work from there to there. I'm oversimplifying history here, but really these two papers are where this scaled to very high systems. BPOD means balanced proper orthogonal decomposition. Proper orthogonal decomposition is just what physicists call principal components analysis. So it's all connected. Good. Okay, so now I want to tell you about essentially how you would do this without ever computing any gradients, because this is, at the end of the day, what's actually important to us is not actually computing gradients. Okay. Good. Okay, so we're going to essentially find the leading R columns of T, the stuff that we want, the balancing transformation into these balanced coordinates. And we only want the first R columns of this because we want a reduced order model of rank R. So what we're going to do now is, instead of ever cooking up these gramians, we're going to work on this assumption, or this innovation, that I can basically directly take the singular value decomposition of O times curly C, the controllability matrix. So instead of building these empirical gramians or a rank truncated version of these empirical gramians, what I'm going to do directly, this is what Rowley did, was I'm going to compute my direct modes. I'm going to compute my my direct impulse response and my adjoint impulse response, stack those into matrices C and O, curly C and curly O. And then what I can do is I can multiply these directly. I can just, bam, multiply them together and work only in terms of this quantity here to get my reduced order model. And this is called balanced proper orthogonal decomposition, or BPOD. And remember, POD is just physicists' way of saying PCA. They're kind of all based on the singular value decomposition. Okay, so SVD, PCA, POD, and there's about 5 other names for this, because it's that important. Many people have developed this for fields along the way. Okay, so right now what we're doing is we're trying to compute the leading R columns of the balancing transformation T using this product O times C. Now what's cool is you can write this O times C. If I actually expand this out, what I get is, now this is going to be a little crowded. Okay, so O is C, CA, CA to some power. And curly C, remember this is my system matrix C, it's different than curly C. Curly C is B, A, B, A to some power M, B, okay? And if I write this, if I multiply this out, these have the right dimensions that I can the inner dimensions match, so I can multiply this out, and what I end up getting is this big matrix that's called a Heinkel matrix, H. Now remember our Heinkel singular values? That's going to come into play here. So I can multiply this out, and I get CB, CAB, CAB, CA squared B. This will be CA cubed B, and so on and so forth, and so on and so forth. So CB, CAB, CA squared B, CA cubed B, and so on. This is just a big symmetric matrix called the Heinkel matrix. Let's put that Heinkel, very important. Should be reminding you of the Heinkel singular values, okay? And so this Heinkel matrix, we're going to come back to this later when we talk about the eigensystem realization algorithm, but I just want to plant this idea in the back of your mind. We built our controllability matrix and our observability matrix assuming that I could measure my full state X and I could run this adjoint simulation. So we're doing this in a simulation where we can measure the full million-dimensional state X as it evolves in time, and we can run this non-physical adjoint simulation to get these two things. But what's really cool, and we're going to come back to this when we talk about eigensystem realization algorithm, so let's just put a little note in that. Eigensystem realization algorithm will be a lecture in a few lectures. If I gave an impulse in U and I just measured Y, I couldn't measure the full state X, but I could kick the system in U and I could measure my measurements Y. This would essentially be Y at time 1, Y at time 2, Y at time 3, so on and so forth. This would be Y at time 2, Y at time 3, and so on. So I can, long story short, I can actually compute this Heinkel matrix from real experimental input-output data without ever having access to X or my adjoint system. Okay, and so we're going to talk about that in the experimental context later in terms of ERA. But for now, we're going to assume that we have access to our equations. We have access to adjoint equations. We can measure the full state, and we have these big data matrices. Okay. Okay, this is pretty hairy. Okay, we're going to fill up the whole board. So what we're going to do now is we're going to take this Heinkel matrix, and we're going to take its singular value decomposition. Okay, we're always going to rely on singular value decompositions to make our lives easier. So we're going to say this is U sigma V complex conjugate transpose star, just a transpose for real matrices. And what I'm going to do is I'm going to decompose this into different components. I'm going to say there's U tilde, the stuff I'm going to keep, the first R columns of U, and then all the stuff I'm going to truncate. This is just like what we did before. My sigma matrix is diagonal. These are my Heinkel singular values, my HSVs, my Heinkel singular values. I'm going to have sigma tilde and all the sigma stuff I'm going to truncate. And then finally, I'm also going to have V. How do I want to write this? I want to write this as a column of V tilde star, and then all the stuff I'm going to truncate. No tilde, just truncate. Okay? So basically what I do is this is my direct impulse response. This is my adjoint impulse response. Okay, I compute these in a computer, my direct and adjoint. I multiply them together to get a Heinkel matrix, and I take the singular value decomposition. And basically, the singular values here are very, very related to these diagonal elements of my balanced Gramian here. Okay, so these are the same Heinkel singular values there. And this, again, then tells me how do I chop this system up to only keep the first R portion of this model. Okay. Whew, all right, a little bit longer. We're going to write down the last step now. Okay, remember, I just wanted the first R columns of T and its inverse. And so that's what I get here. So now what I can get is my direct modes. I think in the past, what I did was I called these psi. So what psi equals is it equals curly C times V tilde times sigma tilde to the -1/2. There's some math. You can kind of convince yourself that this actually matches what you got with balanced truncation. That's a really nice exercise, or you could read about it in Rally 2005. It's really nicely outlined there. It's also in our book. Okay, and then you can get our adjoint modes. And we're going to call these phi. And phi are going to equal curly O star U tilde sigma to the -1/2. Okay, so these are literally the first R columns of this balancing transformation. And these are the first R columns of the inverse transposed. And then the last, kind of the punchline of all of this, is that I can use these to actually get my reduced order model. So I'm just going to show you how you do this, because it's super nice. Then what I can do is I can say, OK, A tilde, B tilde, C tilde equals. OK, I'm going to recap in a minute. So if you're feeling like this is just overwhelming, we're going to just do a recap. This equals phi transpose times my original A times psi. This equals phi star B, and this equals C times psi. And I think if you go back to the balanced truncation lectures, that's exactly what we found, is that if I take the first R columns of T and I call those psi, and I take the first R columns of the inverse and I call those phi or phi star or whatever, then this is how you get your reduced order model. This is my my order R reduced order model. Okay, so let's do a recap. This is really cool. So why did we go through all of this math? We went through all of this math because although Moore had the right idea of finding, so before Moore, people didn't think of degrees of controllability and observability. There were these rigid definitions of it is controllable or it is not controllable. What Moore said was there are degrees of controllability that are given by kind of these directions of the Gramians. Okay, so Moore allowed us to hierarchically arrange our state space in a new coordinate system so that we could get a reduced order model in terms of the most controllable and observable directions in state space. So that gives us a reduced order model that we could do control with. But that involves computing these gigantic n by n Gramians, which is ridiculous. We don't want to do that. So what Moore did was he said, okay, if you have a direct system and an adjoint system and you can collect data from these measurements, you can approximate your Gramians and you can do this procedure. Still very expensive. So Wilcox and Prairie said, well, I don't have to compute this entire rank n by n Gramian if I only want the first r columns of T to get psi. So they did a rank R truncation of this. And then Rowley 2005 kind of came up with this expression that you didn't actually have to work with these empirical Gramians at all. What I could do is directly work with this Heinkel matrix, O times C. And this is a lot better because this, O is a lot smaller than these Gramians, and C is a lot smaller than these Gramians. When I multiply them together, I get this Heinkel matrix. I can take the SVD, and I can get a reduced order model. Okay? So you still need a direct and adjoint simulation. You still need to collect that data. But then you can build this Heinkel matrix, SVD it, and get your model directly. So this is a pretty streamlined procedure to getting reduced order models without ever building these Gramians. Okay, so one of the things we're going to talk about next is I drew this red dot. That was supposed to be my sensor Y, and I had U is like the angle of attack of this airfoil. But in many systems, the measurement Y is actually very high dimensional. I can measure the whole state X, so I might have 1 million measurements. I can't do an impulse response in every single one of those million pixels or million grid points in my simulation. I can't store 1 million impulse responses. So in the next video, I'm going to tell you about what Rowley did in 2005 to handle that case where my number of outputs was massive. Okay, so to kind of bypass doing this, this observability impulse, this O impulse response for really, really high dimensional output data. Okay, still data driven. You have data, you get models, but it's based on an equation. You have to have access to the equation. Okay, thank you.